up and down, and you want an output which ideally should be flat, right? You want an output like this. You don't get that. You get something which looks like this. At least for a half-wave rectifier, that's what you get. But your aim essentially is this flat thing, right? So what you want really is the DC or average current. You don't really want the entire power which is flowing in. So what should go in the numerator here should really be IDC square R. Not the entire I square R, but only the DC current square R, because that's the power that you want. You also get a lot of extra power dissipated at the resistance, but that's really something which you don't really want. And what about the denominator? The denominator essentially has to be how much power does the source deliver. Now, this is where you have to take into account the entire current which is flowing through the circuit. The reason why I am telling you this as an answer to the diode clamper question is that this is also a hint. This is a simpler problem, but there also to realize that the power delivered by the source is the entire current which is flowing out of the source times the source current, source voltage. So what you should have here is IRMS square into R plus the diode forward resistance, because there's some drop across the diode as well. But if you ignore the small rd, basically the efficiency is basically IDC square by IRMS square. And IRMS square, of course, is also, this is a result which is there in, which you had to prove in this current questionnaire, is I ripple square. So this is another reason why we hate ripple. If you have more ripple, you're going to have less efficiency. But that's easy to understand. If you have more ripple, that means much of the power that you are getting is in the form of fluctuating current, which you don't really want. Okay? So this is of course an approximation where we can ignore the dissipation of power in the diode. But anyway, that's a pretty good approximation usually. So you can ignore this, and then of course you can cancel R and RD, both R's together, and you end up with this result. Now you have to think along similar lines when you think about the diode clamper. How much current is the power source actually delivering? So I'm not giving you the answer to this, but this is a good question. You should think about it. But I've given you enough of a hint to think about it. So, next question, if there's any. Okay.
Sir, so in the voltage multiplier, we can essentially keep on adding those.
You can add more and more cells and create higher and higher voltages. You can, of course. Of course, you have to realize that the diodes will have to be able to withstand that amount of reverse voltage.
Yes, but theoretically we can, like from a finite voltage, we can get infinite.
Yeah, but the current keeps on decreasing at every stage. You get less and less. So the power essentially is not hurt that way. You get.
So we can't find it like V RMS. Then we have to define it as V into I, right?
Always that
power.
Right.
Okay, yeah.
And it's always V into I. Okay. And ultimately, this kind of, in fact, what you are describing is actually what is used often, or at least was used very extensively in the early days of linear accelerators, when you build particle accelerators with huge voltage, trying to accelerate particles to very high energies. You needed very high voltages, but no. All you needed were high voltages. You didn't need big currents. You needed to establish a large potential difference, and that was essentially done by something called the Cockcroft-Walton circuit, which essentially is a voltage multiplier with many such cells. It will produce reasonably high voltage, but at low current. And the point is in principle there is no limit, but in practice the limit simply is that you have to be able to ensure that the diodes can provide enough hold the huge reverse biases. But you can easily go to few tens of thousands of volts using this, and you do. This is one of the standard circuits used in small energy, low energy particle accelerators. Okay. Now, if there's no other question, I'm going to actually introduce you to a new topic today, but let me wait for people who have actually asked questions. Okay, somebody had the presence of mind of starting the recording, right? I didn't. Thank you, whoever did that. I hope I didn't do it by instinct and forgot all about it, but I believe one of you did. Ah, good. Thanks. Okay. Next question.
Sir.
Go ahead.
In the limiter circuit, when we are placing two diodes,
you are essentially placing
opposite bias.
Two diodes which are connected in opposition, but in parallel. Yeah, that's what you're doing.
Yeah. But in if we were using them independently, they would have very different outputs than what we are doing when they're together. Confusing me.
True.
Suppose one.
Okay, in case you are talking about the superposition principle, are you going to say why can't we add the result for one at a time? Sorry, I
was kind of thinking along with
Yeah, but superposition principle works only for linear circuits. Diodes are inherently non-linear, in fact extremely non-linear circuits, and so superposition principle doesn't stand a chance there.
Okay. But even if we ignore superposition, could you even just go again through why exactly is the profile coming out as it is? I'm not very clear of
no, but
why.
This is sort of straight. First of all, what you have to realize is this: when a diode is forward biased, first of all, you have to remember that a diode is not ideal. If a diode is ideal, if this diode were ideal, then there are two possibilities. If you forward bias it, it will actually have zero voltage drop across it. Some current, whatever current, the current of course will depend not on the diode but actually on the other circuit element that is connected to it, right? If you connect a resistance R, that resistance decides how big a current you are going to get through the diode. But the drop in voltage across an ideal diode is always zero when it's forward biased. And when it's reverse biased, how much is the drop?
Equal to the voltage being applied.
Equal to the input voltage, because no current flows, and since no current flows, the resistance drops nothing. Okay. Now this is something which takes some getting used to, because although we all know this in theory, very often people tend to sort of get confused about this, because how come no current means high voltage? But you have to remember, no current means no current through the resistance, hence no drop here, so high voltage, right? So no current here means high voltage here. Fine. But that is the ideal case. Ideal case means no drop whatsoever in the forward direction. Okay. Now, here on the other hand, you have to have if you have a non-ideal diode, say you can approximate it by this effective circuit that we talked about. An ideal diode D, a V gamma cut-in voltage, and a small resistance which for most purposes can be ignored. Now V gamma also can be ignored provided your voltages are big, but V gamma typically is of the order of 0.7 volts to 1 volt depending on what kind of a diode you are using. So for pulse shaping activities, the kind of thing that you use this for, you usually use small signals, small voltages, and their 0.7 volts can be substantial. You cannot really ignore it. So the idea is, this is again something that simply used as a rule of the thumb, that when a diode is forward biased, it drops 0.7 volts. When it's reverse biased, it drops the entire voltage. Okay, so that's the basic idea. Whatever voltage is possible. Now, if you have two voltages in parallel, then what will happen? Then either this side is positive and this side is negative, in which case this diode becomes forward biased. At the moment this diode becomes forward biased, current flows through it. And if you are forward biased, and of course no current will flow through this one because this is reverse biased. So how much is the voltage drop across this one?
V gamma.
V gamma. Okay. But when will this be forward biased? Not when this voltage is positive, but when this voltage exceeds V gamma. Right? You need V gamma amount of voltage to go into forward bias. Before that, the diode doesn't go into forward bias. Okay. This is the situation with real diodes. So once voltage exceeds V gamma, this diode becomes forward biased, and then the voltage drop across this will simply be V gamma. It will not budge from there. What happens with the other diode? The other diode, of course, carries no current. Since it is connected in parallel to this strip, whatever voltage occurs across this, the same voltage must appear across this. Right? This plays no active role in changing the voltage or setting the voltage. Whatever voltage this forward bias diode gives it, it happily takes that. Right? In reverse bias, whatever the diode itself is off. So it plays no role in converting, in conducting or changing the voltages. But that's for one half of the cycle. So when the input goes this way, suppose this is our input, let's say. And one good thing about pulse shaping up is I don't even have to worry about drawing a nice sinusoid, because frankly the pulse could be any shape. Doesn't have to be sinusoid. Okay, so if this is your input, once the input goes above V gamma level, the output is fixed at V gamma. But what happens before that? Or let's say if it goes below minus V gamma, then what happens? Then this diode gets reverse biased, this gets forward biased. So now voltage drop appears across this, and of course here the voltage drop is V gamma with this side positive, this side negative, which means minus V gamma according to our convention. So the voltage then stays. So when the input voltage goes beyond minus V gamma on this side, the other diode gets forward biased and you get minus V gamma across that. What happens in between? In between, neither of the two diodes is forward biased. Okay. Both are reverse biased, neither carry any current. So in this part of the circuit, there is no current whatsoever because both diodes are forward biased, reverse biased. So no drop appears across this resistance. So whatever input you give, that's the output you get. So in between, the output exactly follows the input. So that's the situation. So once you cross V gamma, so basically this is like a clipper. You know, this diode would essentially clip the top off. It will just say that there is no output when the input is positive. That sounds a bit crazy because diodes actually conduct when the input is positive in this case. But remember, we are looking at the voltage drop across the diode itself as the output, right? So if this were, by the way, if this were made out of ideal diodes, then they would always be forward biased. Either one or the other would always be forward biased because you don't need a cut-in voltage there. And then what will happen is these two diodes together will basically always work like a short, right? Either one side is shorted or the other side is shorted. And you put them in parallel, that means the overall thing always needs, that's like just putting a short across this, which means no current, no voltage drop will ever appear across that. That's why it's a good thing that diodes are not ideal. With ideal diodes, you would not be able to build a limiter like this. Of course, instead of this bias which is there because of V gamma, you can also put in actual voltages, batteries to bias things, right? And if you do that, then the circuit will essentially take, so if you put a diode here and put an opposing voltage, let's say of 2 volts here, then this diode will only conduct if the input goes beyond 2.7 volts. I'm assuming cut-in voltage is 0.7 volts. And so once it goes beyond 2.7 volts, once the input goes beyond plus 2.7 volts, they may be up here. Once the input goes here, the output stays flat at 2.7 volts. That's because there's a 2 volt drop across the battery and an extra 0.7 volts here across the diode. So you have a net 2.7 volts drop. And if you make the circuit with, this is of course not a limiter, this is just a clipper. It just clips off the top beyond 2.7 volts. But if you make the circuit with another diode with a battery facing the other way, let's say this is 3 volts, then this will conduct only if minus 3.7 volts is crossed by the input in the negative direction. So only if the input falls below minus 3.7 volts. And if it does that, the output will be fixed at minus 3.7 volts. So only if the input drops all the way to minus 3.7 volts will the output clip. But what happens in between? So if this were the input like this, what happens in between is neither of the two diodes is forward biased, simply because these reverse biases are too big. Both of these diodes, you realize, have been reverse biased, right, by the batteries that you have connected. And the reverse biases provided by the diodes is too big for the input to overcome them. And then the output simply follows the input because there is no current in the circuit. Okay, so this is basically what you're going to get. That's the limiter with bias.
Okay.
Okay. Now any further questions? Because I want, yeah, go ahead.
So when you calculated the ripple factor during the starting of the video,
Yeah.
so you considered that the capacitor discharges at a constant rate, right?
Yeah.
P by R. So
Yeah.
from that, when we are considering that the output is constant, how can we calculate the change from something which is
So that of course is an approximation. You should realize that the current, of course, will be voltage across the capacitor by R, right? Because what you have is a diode on this side, but the diode is reverse biased, so this input side is cut off. You have a capacitor here, and you have a resistance. And once the input has declined below its peak value, the capacitor, which had already charged to the peak value, now slowly loses the charge through this resistance. Okay? So you're right that the current has to be the voltage across the capacitor, or which is of course the output voltage, by R. And as the capacitor discharges, the output voltage goes down, so the output current also goes down, and as a result, what you end up with is an exponential decay, right? So just forget about the diode for the time being. If you just had a charged up capacitor and you had connected a resistance across that, the output would look like this. Why does it look like this? It looks like this because initially when the voltage is large, there's a large current through the resistance, so the capacitor loses charge rather rapidly, and as the capacitor loses charge, its potential decreases, the current goes down, and hence the rate at which it loses charge also goes down. So initially it comes down, the voltage comes down steeply, and then the voltage flattens out, right? You all know that, and that's why you have this differential equation to solve, and you get an exponential decay and so on. However, at the very beginning, what you can always say is, of course, the voltage is changing. It's no longer the peak value, but it's changing little. So I use Vp by R as an estimate for the current, and I said that this is an estimate. It's not exact. But I did say at the beginning of the video that the Vp by R is just an estimate. It's not exact. But as long as our circuit is any good, and we hope our rectifier circuit is good, at least the filter really works, what we expect is the output should not really go up and down rapidly. It should go something like this, right? It is coming down, but coming down by a very small amount. So should I use a VP by R? Actually, no. The actual ripple. So you are right in the sense that what I've got is an overestimate of the ripple. When I calculate the ripple by saying, okay, VP by R, let's take that to be the current, and multiply that by the time period T. VP by R into time period T, because that's the time for which the capacitor is losing its charge. And so this is a net charge lost, and then I divide by C and say this is the V ripple peak to peak. You must realize that this is an approximation, number one, and it's an overestimate. Why is it an overestimate? Because the current is really not VP by R throughout, it decreases a bit from there. And also the time for discharge is not capital T, not the time period. Even for a half-wave rectifier, the capacitor charges up again once the input voltage crosses the capacitor voltage, right? And the diode becomes forward biased again. And that would mean that even if you had a half-wave rectifier input which goes like this, the capacitor does not discharge all the way from here to here, not for one complete time period. It discharges up to this, after which it sort of charges up again. Okay. Now, so capital T is an overestimate as far as the time for discharge is concerned. VP by R is an overestimate as far as the current is concerned. But this is fine, because what we are going to say is that whatever our circuit does is not going to be worse than this. And moreover, if my circuit is any good, the ripple should be very small, which means although voltage does change from VP, it should not change very much. So VP by R is a reasonable approximation. Once again, let me point out that this is a theme that I'm saying over and over again. Electronics is one place where you have to learn how to make approximations. And if you're not satisfied with this, you have to do a more precise calculation. By the way, the more precise calculation is in your next assignment. That is, if you want to get a more precise estimate of the ripple factor, how would you proceed about it? However, so that's why I will not describe to you how to do it, because it's your assignment for the next part, next week. However, you will realize that at the end of the day, after you do, one of the reasons why you should do that calculation is that you will realize that only if your rectifier is rather bad, if it has a huge ripple, will your estimate from this simple-minded calculation that you're doing here go substantially wrong. The more precise calculation will of course take a bit more effort. So you will have to take the fact that the shape is not really a straight line, it's a exponential curve, so you have to estimate the RMS value for that. You will also have to use, so it's not really a triangular waveform, but a curved wave. You also have to take it into account that the input voltage picks up and the diode forward biases before capital T time is reached. So again, would you want to do this exactly? The answer is no. You don't want to waste your time doing very precise calculations. What we are going to talk about is the next order of approximation beyond this very simple estimate. Now, whenever you are designing something, ripple is something you do not want. So if you overestimate the ripple your circuit will produce, that actually is not bad. What is worse if you underestimate it, right? So if you were to say that, okay, I have designed a circuit which produces a ripple of 10%. If that's an overestimate, your circuit may actually produce 8%, and 8% is fine. People are happy with 8% then. But if you say your circuit should produce 10% and you end up with 20%, then your circuit is really bad. Okay? So you have to understand the philosophy behind the kind of approximations we are doing here, and that is really very important. It's not really, okay, by the way, let me stress once again, it's not a sign of weakness to approximate. But you have to approximate only knowing fully well what you are approximating. In that sense, this is a very good question. You have to clearly realize that the approximations made are that you have assumed a constant current, although it's not really a constant, and we have assumed that the time for discharge is capital T, although it's not really capital T. Okay, but again, you also know that this should not be too bad. If, on the other hand, let's say RC is time constant for discharge, which of course is a time constant for discharge of the RC circuit, if RC is of the order of T, or T by, say, as I say, even twice T, then what happens is substantial discharge takes place even within one cycle, and so this approximation becomes very bad. Just for a quick estimate, what's the time period for the AC source that we have, AC mains that we have? And how much is the time period?
1 by
1 by
50.
Yeah, 1 by 50, but how much is that? That's 20 milliseconds, right? It is 1 by 50 in seconds, 1/50th of a second, but that's 20 milliseconds. If your time period of your RC circuit, if R times C is 1 second, then 20 milliseconds is very small compared to that. Then your ripple will be rather small, which is what the kind of thing that you're aiming at. So if your load resistance is of the order of a kilo ohm, you would not use a resistance smaller than a millifarad, because a kilo ohm times a millifarad, farad times a ohm is a second. Kilo ohm times a millifarad, the kilo and milli cancel each other out, it's again a second. Okay, so when you design a rectifier circuit, you would have to realize what kind of, you would have to design it with keeping in mind what kind of capacitor values, resistance values you will use. So typically you would have a rather small ripple factor, so this is a pretty good calculation. Okay. Okay, now let me move on to one topic which will set the stage of some of the calculations that we will do next. But one thing that I wanted to talk to you about was how to actually go beyond just, say, the ideal diode approximation and try to understand circuits. In fact, I already gave you 2 computation problems last week, and one of them involved the capacitor filter and writing down a differential equation, solving the thing properly. Now, let me just point out that something like this, for example, this circuit, which I did talk about in the video. Can you recognize what circuit we are talking about here? What is this circuit? Two diodes, 2 capacitors. Anybody? This was one of the pulse shaping circuits that we talked about. In fact, we talked about this twice. That should be a big hint. In 2 forms. Okay, if you forget about this part, this part, so if you say let's say you block this out, just had this circuit. Can anybody tell me what this is? Some of you definitely should be able to tell me what this is. If you did not have the second diode and capacitance. Diode? What? The diode?
Clamp.
So, this is a diode clamper. Right, this is a diode clamper. Okay, good. This is a diode clamper. On the other hand, if you just had this, okay, let me just get rid of the, oops, I went too far. If I just had this part, a diode with a capacitor connected across some source. What is this, by the way? What will this do? What kind of a circuit is this? That is
Yeah, ideal rectifier.
this is, okay, this is really, okay, that's really not the name for it, but I understand what you're saying. If you had a resistance here, you would have a rectifier which actually has a capacitor filter, right? If you had this resistance connected here, that would have been a rectifier with a capacitor filter. If you don't have the resistance, then what happens is that the capacitor, once it charges up, never gets to discharge, right? It doesn't have a discharge path. So what happens is, when the input rises, the capacitor voltage rises with it. So the capacitor voltage follows the input, but once it reaches the peak and the input dies down, the capacitor voltage stays there. So what is this? This is actually the ideal rectifier in that sense. You have used the right word in that precise sense, that the voltage does not even come down. Okay, but this is really no use as a rectifier at all, because a rectifier is meant to deliver power somewhere, so it's meant to deliver current. So you need to connect a load across it. But what this is good for is that this is a peak detector. It can just measure the peak value of whatever input voltage you're giving, right? Because now the voltage which it holds constant at is whatever constant maximum value you gave. In fact, if your input went something like this, suppose your input was, then the output will go something like this. It will follow the input initially, then hold flat, then again follow the input, then hold flat, and until, because once the input exceeds the capacitor voltage that is holding, the diode gets forward biased again and the capacitor charges up, and once the peak is reached, it stays there. So this is what is called a peak detector. It's a very useful circuit because very often you would need to know how much is the peak value of the input where you have an irregular input. And when you put the two together, you have this diode clamper, which is a positive clamper, which essentially pushes the output up, and it pushes it up to. So ultimately what happens is, in the long run, after the first few cycles, if you just looked at this one, for the first cycle, what will happen? If your input goes like this, forget about the peak detector at the end, just the diode clamper. In the first half of the cycle, when this is positive, is the diode forward biased or reverse biased? When this side is positive, what happens? Forget about this part. This part is not there as far as we are concerned. Is the diode forward biased or not? When this side is positive? Yes? Come on, the diode is connected this way. It's easy to see whether it's forward biased or not. Quick rule is just try to figure out which way will current flow. Will current flow in the direction of the arrow? Yes or no? If this side is positive and this side is negative, which is what this cycle means, which way will the current flow? Which way would the current have flown, by the way? Assume that the peak detector is not connected, just a capacitor and a diode. If this side is positive and this side is negative, current would try to flow like this, right? From positive to negative. It can't, because the diode will not allow you to do that. What that means is no current will flow. Okay? So what happens to the capacitor voltage? Yes? That's not a rhetorical question, that's a real question. What happens to the capacitor voltage?
It's equal to the input.
If no current flows, are you sure? I don't mean the voltage here, I mean the capacitor voltage. Voltage across the capacitor. How much is that? Zero, right? Because after all, if no current is flowing, then the capacitor is not charging up. If the capacitor does not charge up, there is no voltage drop across it. But that is the voltage drop across the capacitor. That means the voltage on this end will be exactly equal to the input voltage, right? So that's what this part of the cycle will go like this. The voltage here. What will happen after that? Throughout the capacitor I have zero voltage, right? Then once the input voltage drops to negative values, the diode will conduct, the capacitor will charge up, and the capacitor will essentially voltage will go like this. Initially it will be zero for this cycle, then it will rapidly charge up through the diode, which is now forward biased, until it reaches minus Vp, and after that it will stay there, right? And that means that the voltage up here, the capacitor will always have a large voltage minus Vp. If that happens, what is the voltage here? That's the voltage at the input minus the capacitor voltage. And since the capacitor voltage is minus Vp, the voltage here will be the input voltage plus Vp, minus Vp. And that means after this capacitor has charged up, the entire the output essentially will be the entire input will be pushed up by Vp. So it will go like this. From that point on, it will go up and down like this. That's how the diode clamper works. Okay? Is that clear? So the input, the voltage at this point essentially goes like this. Then it's zero because the diode is forward biased. After that, the capacitor holds its voltage and you end up with just this. Now, having said that, if you put a peak detector after that, what will happen? It will just detect the peak. And how much will the peak be? So if this was Vp sine omega t, what will the peak be?
2 Vp.
2 Vp, right? Because this has been pushed up. So that is why I said this is used. I talked about this twice because it's also the voltage doubler circuit. It produces 2 Vp as an output when just using a half-wave rectifier would have produced Vp. In pulse shaping, its usage is that this is actually used really as a peak-to-peak detector, because a general input may be asymmetric, may be something like this. You may have a small value up here and a large value down here. But the capacitor, of course, charges down until it reaches this voltage and holds that. So the whole output gets pushed up by that amount. Because remember, the voltage here is actually the input voltage minus the capacitor voltage. So when the capacitor voltage goes down to this much negative value, that's the amount by which it pushes up the whole thing. So then the peak value for the resulting thing is going to be actually the peak to peak value for the input signal. Okay. So this is why this circuit is also called a peak to peak detector. Okay. However, let me also tell you one thing. Although this description is right, that the first part of the circuit, let me just draw the circuit again, because I will need the circuit now, actually works like a positive diode clamper, something which pushes the whole voltage up. And the next part works like a peak detector. If you were to follow the actual output of the circuit, the answer, okay, what would you expect the output voltage to depend on time like? So if I were to plot the output here, which is this voltage at this point against time, what would I expect? I expect this thing to essentially, the output of this point, if you had only this, to go like this. Push up to 2 Vp. Then what do I expect the output of this thing to be? Well, if it's really a peak detector, it should go like this, right? It should essentially go like this, then flat, then this, then holds flat at 2 VP. Okay, you get my point. The green line here is the output from the diode clamper or positive clamper, and a peak detector always detects the peak. So if you just go by that logic, it should really follow the input until it reaches a peak, then it holds flat, then again it rises until it reaches this peak and then holds flat forever. Right? This is what you would expect. Is that correct? Did anybody follow this, or has everybody gone to sleep? I expect either a yes or a no to that. Yeah.
Sir?
Yeah.
Sir, could you please explain that green curve again? Like
The green curve is a diode clamper output. That's the one I was talking about before. That is, initially, suppose you have this initial circuit signal which went like this.
Sir, so initially the output should be 0, right?
This voltage.
At that part.
No.
Yes, sir.
You right the first time. The capacitor voltage is 0. That means whatever is the voltage here should be the voltage here. Initially, the diode is reverse bias, no current flows. If no current flows, the capacitor doesn't charge, right? If the capacitor doesn't charge, there is 0 voltage drop across the capacitor. That's important. It's always important to realize that voltages are voltage differences. The capacitor voltage is not 0. The voltage difference between the two plates of the capacitor is 0. Right? That's exactly what when you say capacitor voltage, that is what you mean.
Sir, how would the current across the right capacitor vary if we take a sinusoidal input current?
So if you just had a peak detector, you mean? Are you asking in this? Are you asking in this circuit, or are you asking in the
in this circuit? Because my point is that V into I should be equal to the input V into I, right? Like V into I output should be input.
No, that's not really right. That's not really right, because the capacitors can also carry energy, right?
But the total energy should be but capacitor is getting energy from the input itself.
Right. True.
So shouldn't the output energy be always equal to the input energy?
How do you mean? What do you mean by input? The output power would be the sum total of all the powers together, plus the energy.
It's not the input itself.
Yeah, true. That should be equal to the input power, but output power is not just output power. It's also output. What you really want to talk about is the rate at which the energy of the capacitors change. That has to be equal to the input power. Okay. So if the capacitors can store energy, you have to realize that it's really the energy change of the capacitors that you are looking at here.
Okay.
Okay.
Yeah.
So the whole reason why I'm bringing this up is that you should realize that this whole picture that I've drawn here is actually quite wrong. What is wrong about it is this: if I had a diode clamper and clamper alone, the green curve would be the right output curve, no problem. Okay. If you have a peak detector connected to some external signal, suppose the signal was really like this, and you connected a peak detector to it, its output would really be like this. Okay. But since here, when you say this is a diode clamper, you actually assume that nothing else was connected to it. When you say this was a peak detector, you essentially figured out that something else is connected to it, which is giving the unknown signal. Or when you join the two together, you can't really expect it to work in this fashion necessarily. For example, at the very beginning, suppose at the very beginning both capacitors are uncharged, you have just gone into the positive cycle in this whole circuit. And if I call these two diodes D1 and D2, Can you tell me what is the state of the two diodes? Which diode is forward biased, which one is reverse biased? Remember, this half of the cycle means this side is positive, this side is negative.
D1 is reverse biased.
D1 is forward.
D1 is?
Oh, sorry, D1 is reverse.
D1 is reverse biased. That's what we said earlier also. D1 is reverse biased. And what about D2?
Forward biased.
Right. So the moment you connect the next segment, the argument that we made that the capacitor is not going to charge actually is wrong. Do you get that? We started by saying the capacitor will not charge at all for this half of the cycle because D1 is reverse biased, no current will flow. That is of course right when there is no second part of the circuit. But in the second part of the circuit, what will happen is current can flow, right? Current can flow through this. So can anybody tell me what will the voltage be across both capacitors if the two capacitors are identical? Let's say they are equal in capacitance. Can you tell me what will the voltage be in the input? At these 2 points, this one and this one, which are of course essentially voltage drops across the two capacitors. First of all, will there be a difference in voltage between these 2 points?
No,
Why not?
because across D2 the voltage drop is 0.
0, right. We are assuming ideal diodes, of course. We are making things simpler for ourselves. So these 2 points must be at the same voltage because D2 of course drops nothing because it's forward biased. And what about these two capacitors? Can you tell me how much is the voltage drop across this? If this voltage is Vi, of course that's time dependent, but what will the voltage across this capacitor be?
Half Vi.
There should be
Half
something
Vi.
like half.
Exactly, half Vi. You have done this calculation, right? Capacitors in series and so on. Basically same current flows through them, so same amount of charge goes into them. And since we are assuming equal capacitances, that's important here. Same potential drop across both of them, which means Vi has to get divided into Vi by 2 across both of them. So when this is an input signal, at least the output should look initially like this. Half as big for both this point and this point. But then what happens is, once the input signal starts to decrease, then what will happen? Then this is this was at Vi by Vp by 2. This has also reached Vp by 2, just at the point when the input signal just tries to decrease. Now this voltage goes, once the input voltage goes down, what happens? This diode is at Vp by 2, right? This end. But the input is lower.
Line. That will be at Vp by 2.
That will be held flat at Vp by 2 because this diode will cut off. But what will happen to this? Notice that the voltage across the capacitor is Vp by 2, right? This capacitor. And this voltage has gone below Vp by 2, which means the voltage here is actually negative. This voltage is smaller than the voltage across the capacitor, which means this voltage now is negative, which means this diode is now forward biased. So this capacitor will now start following the input and come down. Now the whole behavior is going to be much more complicated than this circuit. This simple-minded theory that we said, think of the clamper followed by a peak detector. The output will be 2 Vp. That is not wrong. That's actually right. After a lot of steps, lot of cycles go by, that's exactly what will happen. Now, a lot of cycles means maybe 10, 20 cycles, maybe 100 cycles. But since each cycle takes 20 milliseconds, even 100 cycles takes only, say even if this were the AC mains, and you were just using this as a voltage doubler, your 100 cycles takes 2 seconds. After that, you will get 2 Vp. But in between, the approach to this 2 Vp is really rather fascinating. And how do you figure that out? Suppose I were to ask you find out exactly how the voltages V1 and V2 change with time. This V1 and this V2. How would you actually find them out? Okay, let me assure you one thing. The conclusion that was drawn in the video is correct. You will get 2 Vp in the long run. But in the long run. Not the behavior that you will see immediately after you switch on the circuit. In fact, immediately after you switch on the circuit, you will see rather unusual and complicated behavior. And if you can understand, in fact, you should be able to understand that just by using the ideal diode model and figuring out which diode is switched on, which diode is switched off. If you can do that, that will be wonderful, because that will also tell you that you have understood diode circuits perfectly. And the other way would be to just write down the differential equations involved, assume real diodes, assume diodes which obey this equation. Write down the differential equation. Differential equation because capacitors are involved, right? So dVdt will be related to the current, and so you get the couple differential equations which you should be able to solve. So next day we will start with this. Next Friday when we have this discussion class, the first thing we will discuss is how do you solve coupled differential equations using SciPy. So that this is a horribly complicated differential equation to solve by hand. Okay, it's an equation which you cannot solve exactly anyway. But you can solve such equations with relative ease. In fact, with hardly any line of code, 3 or 4 lines of code, you can solve the equation if you are using SciPy's differential equation module, which is also pretty important to learn on its own right. But I would urge you to try to figure out at least how to write down the equations in between. Solution will come later, but you should be able to write down the equations. So, what kind of differential equations do V1 and V2 obey? Assuming, of course, the diodes obey this kind of a equation, that the current through a diode is exponentially dependent on the voltage across it. That's again important, is the voltage across the diode. Okay. So anyway, I've run out of time today. Let's stop now unless somebody has any pressing questions. If you don't, we can just call it a day today.
Sir?
Yeah, go ahead.
Sir, when we are asked to calculate the reverse bias current of a diode in different temperature, can we just use the rule of the thumb?
That depends on how accurate you want your answer to be, right? Are you asking, look, a question like this could mean 2 things. Will I give you marks if you do that in an exam? That's one question. That's a useless question anyway. That will, hopefully, when I ask a question in an exam, it should be clear enough what I will allow you to use from the question itself. If it's not clear what I want you to use from the question itself, then it's a bad question. Such questions can of course come in assignments, because then you can explore and find out. But an exam, of course, should have a clear-cut question. The other is, if you want to use it in real life, can you use the rule of the thumb? The answer is yes, depending on how accurate you want your answer to be. If your life depended on the answer, which might very well be true for some real-life practical application, you may want to go beyond the rule of the thumb. The rule of the thumb is basically for getting a quick idea first, and then if you really want to see whether, and rule of the thumbs are usually quite good for the simple reason that you don't suppose your circuit can take a maximum reverse current of, let's say 1 milliampere, then you will not design it for reverse current of 1 milliampere, you will design it for reverse current of 1/10 of a milliampere, let's say. Good designs are never things which push the parameters to the limits. You want to be well within the safe zone. And if you do that, then using rules of the thumb is fine. Okay, so bye today. Let me just stop the recording.